Today we are going to tackle not other than Hermes. Isn't that epic?
The cursed mortal. You don't try to catch me because you know you can't.
Okay, not that Hermes, but a problem from the IOI 2004, one of the most important programming competitions in the world. I hope that's epic enough. This problem describes a grid-like city, where each block in the grid is one by one solved. Hermes has to deliver n messages to n different recipients, with n being up to 5,000. Each recipient of each possible message is one intersection of the city. I will improvise a possible input. Let's also denote each intersection with a number. Hermes starts at the origin. Let's think like this position is 0, 0. Hermes has to deliver all those and message to all those and recipients. However, he has to deliver them in order, but he has one special perk. He only needs to be either in the same X coordinate or Y coordinate, because Hermes can cast a ray of light and that ray of light can deliver the message. For example, he could start here and then move here and deliver the first message, then deliver the second message here, then move to here and deliver another message here, move to here and deliver here another message, and then finally move to 5 and deliver the last message. And the distance that Hermes would have traveled would be only 2 plus 3 plus 5 over here plus 3, instead of having to walk all the way through to each one of the recipients. The problem is, given the points or the positions of the recipient, you need to find the minimum distance that Hermes has to move to deliver all the message. If you need more details about the problem, check a link on the description below. To get most from this video, I encourage you to first try to solve this problem by yourself, and if you are not able to find the solution, you should ask yourself what was lacking in your line of thought and how you could modify your own line of thought to do it better next time. As we did with the previous example, let's review the actions or choices that Hermes can take. One way of thinking in this problem is that Hermes can move in one of these possible 4 directions or send a message. This is not the most practical way of thinking, but I want to show you how to notice that and how to modify this approach to go for the final approach. Now let's think about the restriction. Hermes can always move to any of these 4 directions. However, he needs to be either on the same X coordinate or on the same Y coordinate of the recipient to send the message, and also he needs to send the messages in order. So let's see how to express that in an equation. If K is the number of submitted messages, then Hermes X position should be this, or Hermes Y position should be this. If neither of these two equalities holds, then Hermes cannot send the message. He needs to move in X to here or in Y to here. With this in mind, we could think the state variables could be the X position of Hermes, the Y position of Hermes, and the number K, that is the number of delivered messaging. And we could think on this as our state space, these triplets of numbers. But is that feasible? Let's check how big it is. From the description of the problem, this can have up to 4,000 different values. This other one also can have 4,000 different values, and K can have up to 5,000 different values. It would be 80 times 10 to the power of 9. This is not feasible at all. We need to find another way to do it. So let's start thinking how we can improve this approach. As always, we started this by checking the actions or choices and the restriction. We need to think how to reframe this, or ideally both of them, in order to be able to reduce the size of the state space. For reframing the actions, let's take a look on this restriction. We are considering all possible movements. However, after sending one of the message, this restriction will be holding. So between sending one message and sending the next, it only makes sense to move from one position where this restriction holds to another position where this restriction holds. Let's see how that looks on the grid. This means that it doesn't make any sense to just move doing things like this, for example, but we only need to consider two choices. Either to move from the origin to the x coordinate, or to move from the origin to the y coordinate. These are the only two valid choices, and also it doesn't make sense to move here or to move here before sending a message instead of moving after sending the message. So as soon as it's possible to send a message, just send it. And this also means that the only state that we need to consider are the ones in the following way. And this is because these two kind of states are the only one that could happen after sending one the message. And this observation is crucial. Take your time to reason about it, or even pause the video if you need to. Now, summarizing the choices that we reframed, then for each message K, Hermes has only these two choices: move in X to RXK, or move in Y towards RYK. Now let's remember that the coordinates that we need to consider are only in one of these two ways. Now let's think if we can remap this coordinates to something smaller, something more visible to deal with. So we can use these three variables to fully describe the triplets of number. Axis would mean if Hermes is matching the X position or the Y position of the next recipient. K would be the number of recipients and POS would be the position where Hermes is in the other axis. From this triplet we could map all of the other triplets in the set. Here what would be the size of the state space? Let's see. There could be two axes, X and Y. So it would be 2 times there could be up to 4,000 positions times and there could be up to 5,000 possible recipients, and this would be 40 million. Perfectly feasible for our purposes. Now that we know how to represent the state space, let's draw a diagram with the transitions of states in order to be able to find the recurrence. These are the two possible choices that Hermes can do at each step along the way. Either to stay in the same axis and just move to the next position or change to the other axis. Let's see how that can be seen on the grid. Let's think on this example. Hermes already delivered 2 messages and it's here. That means that he is matching the X position of the second recipient and also its other coordinate, the Y coordinate in this case is 5, 1, 2, 3, 4, 5 here. So he could move to here to deliver on 3 or to here to deliver on 3. What would be the representation of doing that on this triplet? If Hermes decides to move to here like this, then that would mean to change its coordinates in this way, like here. He would be matching 3 still on the X axis. His Y position would be the same and he would have delivered 3 messages. Then let's see what happened with the other choice. He would move on the other axis. He would have delivered 3 messages, but what would be the value of here? Would be the X position that Hermes have here, that is the X coordinate of the second recipient. That means here would be R sub X sub 2 equal to 2. I hope that example was enough to convince you of these state transitions being the correct one. So now, having this state transition, let's go to the recurrence. There are many ways in which we could express the recurrence, but I think the most direct way is trying to find the cost function that would be the cost of the remaining distance for Hermes to travel from a certain state to the end. Finally, this is the recurrence. As you can see, I basically just copied the two state transitions and added to each one how much distance Hermes would need to travel. The only part that was missing was the base case, and if all the messages were already delivered, then Hermes doesn't need to walk anymore. This is the code for solving the problem. I think it's very straightforward. Maybe the only detail that it maybe seem odd is that I added 2000 to each coordinate, and that's because the problem also considers negative numbers, so I'm adding 2000 to make all of them positive. And also I'm moving the origin to 2000 and 2000. At the other times I also computed the optimum using memorization instead of a couple of nested loops. Even when the recursion is simple enough, I don't want to focus my time explaining the order of filling the table. I plan to dedicate a future video to that, but for now that's not my intent. Also, something worth considering is that the original problem is with n up to 20,000 and less memory than the one that I'm allowing here. But the base idea on the official solution is this same exact recurrence that I presented to you. I hope that we will revisit this problem in the future after dealing with filling the table. But for now, you can be sure that the main idea of the solution is the one that we discussed here. This was our last example of dynamic programming focused on finding the states. However, I remind you that these examples are only a guide for you to start to develop skills around this mindset. This mindset of choices, restrictions, or even sub-solutions or equivalents of sub-solutions. But for developing your actual skill, you need to solve a lot of other problems by yourself. And also there are other dynamic programming problems aside from finding the states. So I plan to keep with this series of videos. If you have any questions, you can ask them on the comment below. And remember, keep practicing.